Hello everyone, here we are again back to our chapter 14. So in this section we're going to continue what we've been learning about the NMR signals and how to interpret data to get your complete picture for the molecule. Okay, so we normally use a reference compound. Reference compound is a tetramethylsilane. And then if you look at these, all there are 12 hydrogens. No, 16, 3, 6, 9, 12. Yeah, 12. 12 hydrogens. Okay. And all of them are connected to carbon, and they are connected to carbon which is on silicon. Now all 12 hydrogens are going to be in the same environment, and they are not going to split with each other. So because of that, it would be one signal. And since silicon is a very less electronegative element, so the reference signal will come at 0. Okay, so Tm is a reference compound. It appears at 0 ppm. And then how do we measure the chemical shift? The chemical shift is measure of how far the signal is from the signal for the reference compound, meaning how far it is from the TMS. Normally it's been calculated and given in our spectrum as distance downfield from tetramethylsilane, and you divide it by the operating frequency of the spectrometer. And this is already been calculated from the instrument and will be given to us as a chemical shift. That's what we see those numbers on the x-axis. So in this proton NMR spectrum, we have this compound. And how many different signals do we have? These two hydrogens will be in one region, one signal, and then we have 9 hydrogens in one region. So 2 to 9 ratio would be 2 to 9. So these are called methyl protons, and these are called methylene protons. And these methylene hydrogens are closer to more electron withdrawing group. Because of that, it would appear more downfield, because they are more de-shielded, and then the methyl protons would appear more closer to the TMS signal. The greater the chemical shift, the higher the frequency. So this is the frequency and the chemical shift. Terms to remember: protons in electron poor environments, we call them as de-shielded protons, meaning protons are more open if it doesn't have any electrons surrounding it. Okay, electron poor environments. And we also give the same electrons, they are more downfield, they have high frequency, and they have larger delta values. And then the protons electron dense environments, those protons are going to be shielded by the electrons, and then they will feel less magnetic field, and they are called upfield. They appear at lower frequencies having small delta values. And this is the direction, the ppm, delta, chemical shift, and the frequency increases. And this is the area where you have our reference compound at 0 TMS. Relative positions of the signal. Now if you look at this compound, you can see this carbon, the hydrogens on this carbon, which is close to nitro group, appear at a higher frequency, 4.37 ppm. And then this carbon at 2.07, and this carbon is 1.04. This is the more downfield, meaning more de-shield, less de-shield, and this is the more least de-shield one. Now NO2. NO2 is an electron withdrawing group. Since it's an electron withdrawing group, these hydrogens will be de-shielded by the electrons, because a nitro group will withdraw the electrons away from the hydrogen, making hydrogen is more open to feel the applied magnetic field from the instrument. So as a result, it would align with the magnetic field applied and be more de-shielded, and you will have that signal at a higher frequency. Okay, causes NMR signal to appear at a higher frequency at a larger chemical shift value. The closer the electronegative atom or the group, the more it deshields the protons. Okay. Now, the same molecules you can see here, but the difference is that they are attached to different elements having different electronegativity. We have some halogens, fluorine, chlorine, bromine, iodine. And out of these four halogens, we know fluorine is the most electronegative element. And in fact, fluorine is the most electronegative element in the periodic table, having 4.0. Okay, as you go down, the electronegativity decreases. So fluorine being more electronegative, it would pull electrons away from the hydrogens next to that fluorine and will make it more deshield. So the hydrogens will not feel that much of electrons. So as a result, it would feel more of the applied magnetic field and it would appear at a higher frequency. Okay, more downfield, more deshield. As the electronegativity increases, the frequency of the signal for nearby hydrogens increases. And chlorine is less electronegative compared to fluorine, so it would appear at a lower frequency, 3.5, more upfield. Bromine going to be even more further down, so it would have less electronegative compared to chlorine. It will appear at 3.4. Similarly, iodine is even more down in the periodic table. That would appear at a lower frequency. Okay. So basically, the more electronegative atoms attach to the carbon bearing the hydrogens, that hydrogens will become more deshielded and they have a higher frequency and a higher chemical shift. So these are some approximate values of chemical shifts. So you guys don't have to remember the numbers, but you can refer to the chart and figure out where they appear. Okay. So this is methyl hydrogens. Carbon having 3 hydrogens, 0.85. And this is called methylene hydrogens, around 1.2. When hydrogen attached to 3 carbons, hydrogen attached to carbon, which attached to some more carbons, 1.55. And then a methyl group attached to a alkene group. So you can refer to this table and see where different types of hydrogens appear in the NMR scale. You see here what we talk about with the more electronegative fluorine attached to carbon and this hydrogen fields 4 to 4.5, and with chlorine 3 to 4, with bromine 2.5 to 4, and with iodine 2.5 to 4. And similarly, if you have hydrogens on a carbon that is closer to oxygen, because oxygen is also electron withdrawing group, so it's about 3.3, but it's less than fluorine, so that's why it's around 3.3. Okay, and you can see hydrogens on a carbon that is an sp2 carbon, in other words it's a double bond, so that also have higher frequencies. Okay, and again, so here's something else. So acid functional groups, hydrogen attached to this oxygen can be vary from 10 to 12, but it is very deshielded because now you have electron withdrawing carboxylic group right here. Okay, and then aldehydes hydrogens also next to a carbonyl group, electron withdrawing group, that makes more deshield, having a higher frequency about 9 to 10. And alcohols variable 2 to 5, alcohols on benzene, phenol 4 to 7, and then the benzene hydrogen 6.5 to 8. Okay, and we'll learn more about why these groups have a higher frequency compared to the other ones. And here's showing the range from 9 to 12 is aldehyde hydrogens and carboxylic hydrogens. And then the benzene hydrogens appear between 6.5 to 8. And vinylic hydrogens, meaning hydrogen attached to sp2 carbon with the alkene group, between 4.5 to 6.5. When hydrogen attached to a carbon which bears electron withdrawing group or more electronegative group, oxygen, nitrogen or any halogen, they ranges from 2.5 to 4.5 depending on the halogen type. And then the allylic hydrogens, allylic means that hydrogen on carbon, and then this carbon is not the double bond but the adjacent one, so we call it as allylic, and this is vinylic. So allylic, or like this, okay, sp2 carbon is the next one, so that appears between 1.5 to 2.5. And saturated hydrogens like this can go from 0 to 1.5. Now you will see here that the hydrogen attached to carbon, but depending on the carbon, what kind of other atoms attached to it, the chemical shift can change. So methane is at a higher frequency than methylene. Methylene is at a higher frequency than methyl. So these hydrogens, where the hydrogen attached to a carbon, of course, and then this carbon has 3 other carbons. We call this hydrogen as methane proton. And then when you have a hydrogen attached to a carbon that has 2 carbons attached, we call it as methylene proton. And when hydrogen is attached to a carbon, it has only 1 carbon and then the rest are hydrogen. We call them as methyl protons. Now out of these 3, you can see methane protons are the more d-shielded. More meaning this hydrogen is less electron denser compared to this or this one. How is that happen? What is it with carbons that makes it carbon when it is all carbons that the hydrogen is more d-shielded? That is because if you recall the electronegativities of carbon and hydrogen, carbon electronegativity is 2.5 electronegativity value, 2.5, whereas hydrogen is 2.1. So which one is more electronegative? Carbon is more electronegative. So in the methane proton there are 3 carbons that are electronegative, whereas methylene proton there are 2 carbons that are electronegative, and hydrogen is the next one. And in the methyl proton it has only 1 carbon that is electronegative compared to carbon. So remember we talk about how the signal appears. The more d-shielded it would appear at a higher frequency. So due to this, due to the carbon being electronegativity, more electronegative, the electron density would pull towards carbons, making hydrogen more d-shielded. So as a result, methane proton would be at a higher frequency, 2.5. Methylene protons would be 1.2 and methyl protons would be at 0.85. Okay. Relative positions of signals continued. Now let's look at here. We have this compound ethyl methyl ketone. Okay, so this is a 2-butanone, 1 2 3 4 ketone, right? So but I will talk about it later. But let's see what are the type of signals we have. We can have 1 2 3 signals. You see here 3 different environment. So these 3 hydrogens would be in one environment, these 2 would be 1 and these 3 would be 1. So there are 3 different environments. Now let's see which one is going to be more d-shielded. Now if you look at C, okay, so this carbon, now carbonyl group, this group is an electron withdrawing group, carbonyl group. Okay, so electron is going to withdraw. So since C and B both are next to carbonyl group, they both would have a higher chemical shift compared to A, because A is not directly attached to electron withdrawing group. But how do you know between B and C which one would appear more de-shielded or a higher chemical shift or a higher frequency? Now, if you look at the same concept that we talked about earlier about the carbon being more electron denser, or carbon would be more electron negative compared to hydrogen. So the B carbon has a carbonyl group and 3 hydrogens, but the C carbon bearing hydrogens, those 2 hydrogens over here, they are next to a carbonyl group and also carbon. So 2 hydrogens and a carbon, and then on the B 3 hydrogens. So because of that, C would be the one that would appear more de-shielded compared to B. And this is going to be your methine proton. Remember, methine proton appears at a higher frequency than methylene proton, which appears at a higher frequency than the methyl proton. Now these 2 hydrogens going to be, C hydrogen is going to be the more de-shielded because it has a carbon and a carbonyl group, and then would be the B hydrogens would be the next de-shielded, and then the A would be the least de-shield, which appear at upfield of the NMR spectrum. So if you draw the NMR spectrum as ABC, so C would be this one, and then the B would be this one, and A would be this one, and if this is 0. Okay, A is closer to 0, and then the B, and then would be C. C would be the most de-shielded hydrogen atoms, 3 signals. Okay, and then let's look at 2-methoxypropane. There are how many different signals we have here? So these hydrogen would be one signal. This one hydrogen would be one signal. These 3 hydrogens and these 3 hydrogens are going to be the same, right? Because those are attached to a carbon which has a hydrogen and a methyl group. And in doubt, you can always draw them in the expanded form. Oxygen, and then you have a carbon, hydrogen, a methyl group, CH3, and a methyl right there. So these are your A methyl groups. So both A's, hydrogens, are connected to a carbon and hydrogen. Carbon that has hydrogen and a methoxy group. So they are in the same environment. So AA, see it, there are 6 signals, not 6 signals, 6 hydrogens in signal A, and then one signal for hydrogen C and another one for 3 hydrogens that is labeled as B. Okay, and out of these A, B, C, which one do you think would be more de-shielded? You're going to look at what is more closer to the electronegative atom. Oxygen is right there, more electronegative. And then the 2 carbons right next to oxygen is this carbon and this carbon. And then the hydrogens on those carbons, B has 3 hydrogens, but the C has 1 hydrogen and then 2 carbons. So the C would be more de-shielded because C hydrogens are connected to oxygen. C hydrogens, yes, are connected to oxygen, and then it also has 2 methyl groups, electron withdrawing, compared to hydrogens. So C would be more de-shielded, and then the B, and then would be A. Okay, so if you draw the chemical shift signals, and then the C would be like this with 1 signal, and then you have B with 3 hydrogens, and then A would be 6 hydrogens. A, B, C. A carrying 1 hydrogen, and then B carrying 3 hydrogens, and C carrying 6 hydrogen signals. But they can also split. I haven't talked about splitting yet. Okay. Protons attached to sp2 carbons. sp2 carbon is basically has a double bond. Okay, now this is benzene, right? This hydrogen is connected to carbon and this has a double bond and it is a benzene ring, and they appear at 7.3 ppm. And then these hydrogens and this hydrogen, they are attached to a sp2 carbon. So they range from 4.7, 5.3, like that. Again, this is going to be more D-shield because it is next to a double bond as well as another carbon, whereas this one carbon and two hydrogens. So between these two hydrogens, this hydrogen would be more D-shielded. And then the hydrogen directly attached to a carbonyl carbon, that around like aldehyde, it appears around 9 ppm. Okay. The chemical shift of protons attached to sp2 carbons appears at a higher frequency than one would predict due to diamagnetic anisotropy. Okay. Now let's look at what is this diamagnetic anisotropy. Why they have a very higher frequency compared to other types of hydrogens. The protons show signals at higher frequencies because they sense a larger effective magnetic field. You see here in the benzene ring there is a pi cloud above and below the plain benzene ring. Okay. Benzene ring protons. The magnetic field induced by these pi electrons of benzene ring in the region where benzene's protons are located is oriented in the same direction as the applied magnetic field. So this is the applied magnetic field, and then the induced magnetic field is in the same direction as the applied magnetic field in the region where the protons are located. So what is going to happen as a result? As a result, the protons sense a larger effective magnetic field because now both of them are aligned in the same direction. Okay? Protons sense a larger effective magnetic field, and then the sum of the strengths of the applied field and the induced field together makes having proton appear at a higher frequency. Because frequency is proportional to the strength of the magnetic field experienced by the protons. So the protons show signals at higher frequencies than they would if the pi electron did not induce a magnetic field. So the pi electron field and also the applied magnetic field align as a result. So the hydrogens are going to be more de-shielded and it's going to feel more frequency and appear at a higher chemical shift. Same thing happens in alkenes. So alkenes also we have a pi bond. Okay. The magnetic field induced by the pi ring, this pi ring, pi electrons of an alkene or by the pi electrons of an aldehyde, same thing with the aldehyde. So in aldehyde you can see where the protons bonded to sp2 carbon right here. They also orient in the same direction as the applied magnetic field. You see the same orientation. These protons too show signals at higher than expected frequencies. So because of that, alkene hydrogens and carbonyl hydrogen, that is like aldehyde, would appear at a higher frequency. Induced magnetic field is in the same direction as applied magnetic field in the region where the proton is located. And if a hydrogen is bonded to a sp carbon, I hope you remember what are sp carbons, which is when you have a carbon with a triple bond. So these hydrogens, They are called alkyne protons. But you can see in contrast, the chemical shift of a hydrogen bonded to an sp2 carbon is at a lower frequency. It's about 1.9, whereas alkene is between 4 to 6, right? But alkyne is about a lower frequency. Okay, it's at a lower frequency than one would predict from the electronegativity of the sp carbon. And that is because the direction of the magnetic field. So this is the direction of the magnetic field. Okay, induced by the alkynes cylinder. So alkyne, so this is the alkyne. If you draw this alkyne like that, you can consider it as a cylinder. The direction of the magnetic field induced by the alkyne cylinder of pi electrons in the region where the proton is located is opposite to the direction of the applied magnetic field. So the proton sends a smaller effective magnetic field and therefore shows a signal at a lower frequency than it would if the pi electrons did not induce a magnetic field. Okay? Because the induced magnetic field subtracts from the applied magnetic field. So we can start the integration in the next session.